Yes, sir. We are live now.
ठीक. So I can explain now from here.
Yes, sir.
So there are two questions. One is by Mr. Prem Ranjan. He is asking the questions from assignment number 1. So question number 6 and question number 8, he wants to understand what is the uh, reason for selectivity. So I'll explain that now. What I have expected was the answer to be 2 and 4. So basically, when this compound is heated, so it will undergo sulfoxide elimination. So there are 3 protons or 3 hydrogens which this oxygen can take. One is this particular hydrogen next to the phenyl group, which is benzylic and tertiary hydrogen. This is also tertiary, but it is next to the methoxy group. And this methyl hydrogen is a primary hydrogen and is obviously sterically unhindered. Now, what happens that normally it will be the abstraction of this particular proton will be first that will take place. And once that takes place, then you would get elimination. The hydrogen from here will eliminate, and then sulfoxide will go along with the hydrogen. So you will get a double bond CH2. So this should be one product. And the other product now is between elimination of this benzylic hydrogen versus this particular hydrogen. Both are tertiary. And if this hydrogen abstraction occurs, then you would get the product number 4, which is now, as you can see, it is in conjugation with the phenyl ring. So the extended conjugation and along with the methyl group, the double bond is very stable compared to even this particular, the number 2. So this product will also form. Now, if you are heating it, then of course, partially this particular product number 2 can also get converted to the product number 4 because that is thermodynamically more stable. Now, the question comes whether why are we not getting the product number 3? The reason is that this hydrogen, which is next to the O-methoxy hydrogen, which is also a tertiary hydrogen, when this oxygen of the sulfoxide comes in close proximity of the hydrogen which is next to the methoxy hydrogen for the elimination of the sulfoxide to take place, then it encounters the lone pair of electrons on the oxygen here. So the anion, the sulfoxide ion here will come very close to the lone pair of electrons on the methoxy, and there will be electronic repulsion, and therefore approach of the sulfoxide oxygen toward this particular hydrogen will be not easily possible, and that is the reason why we get product number 2 and product number 4. Now um, the question number 8, I will again share the question number 8, and just I will stop sharing and again take the question number 8. Now the question number 8, uh, let me start sharing. How come it is not coming? Question number 8, just come here. Not able to get this screen share. Select the window. I'm not able to get this. ये यहाँ पे है. So I should be able to share this. Oh, now it has come.
Sure.
Okay. So Now, oh, it's not coming. इस पे नहीं आ रहा है यूट्यूब पे. नहीं आ रहा है इस पे. हेलो.
Yes, sir. Question number 8 is visible.
हाँ, but 8 is not coming. I'm trying to share it, but
Yes,
you are
it's
sharing your
visible to me,
application.
sir.
Uh, it should come on YouTube. It's not coming.
Yes, sir. There is some delay. That's why it's visible, sir.
Huh?
We can proceed further, sir.
Proceed further.
Yes, sir.
Actually, I want to show that question number 8. I have shared that particular one, but I'm not able to see that. Share. No. I have to share the screen. Screen, window, share. So in question number 8, basically, I'm not able to see that screen. The molecule which I have shown here is having a locked tertiary butyl group, and therefore it will have a conformation in such a way that the tertiary butyl group will be equatorial. And obviously, this particular molecule, which has a chiral center at the carbon, which is having a tertiary butyl group, is a racemic compound, because we have not taken this as a optically pure compound, as we have written already there in the question that there is a racemic. So even though the methyl group can attack from whichever side, say from the axial side, then it gives you product B, and if it attacks from the equatorial side, it will give product A. So it doesn't really matter from which side it attacks. It is still going to give a racemic product, because the starting material is racemic, and therefore uh, I have written here in the solution that since the starting compound is racemic, its mirror image is present in equal amount, even though methyl magnesium bromide attacks from equatorial side to form A and from axial side to form. Corresponding mirror images are also present in equal amounts. So hence, A and B both will be racemic. Now there is a question, as I have shown it here, like here. So since this is starting material is racemic, and therefore the products would also be racemic. Even though supposing we say that okay, the equatorial attack takes place and A is a major product, say 90% or 95%. Even then, since the starting material is present in equal amount as a mirror image, therefore the product will also be racemic, and its mirror image will be also be present. Now there is a question by Dr. Niranjani. She says, what type of oxidation and reduction related questions mostly asked in CSIR net exam? Any trick there to find out easily and solve them? Well, let me explain that the questions would be mechanism based. There can be any question, but there can be mechanism based questions. So all the mechanisms have to be properly understood. Then generally the questions will be based on stereochemistry or stereoselectivity or any selectivity in general. Can be stereoselectivity, can be regioselectivity, can be chemoselectivity, can be diastereoselectivity. Selectivity. Just as I gave an example of the methyl magnesium bromide addition to the ketone that I showed in question number 8 of the home assignment. So obviously, such a question can be asked. So if suppose instead of adding methyl magnesium bromide, suppose if you add lithium aluminum deuteride or hydride, so obviously a similar type of thing will happen. And when we study the when you study the reduction part of it, a lot of stereochemistry is going to be talked about it. Then there can be a combination of oxidation and reduction. So one can, reduce a compound. For example, you have an ester, you could reduce it to the corresponding alcohol, and then depends on whether there is already an alcohol, and now this alcohol of the ester, alcohol from the ester will be primary alcohol, and if suppose there is already an alcohol which is an secondary alcohol, for example, so now you have two alcohols in the reaction. So I can give a question which is having a hydroxy group and an ester group, and then do the reduction so that you have two different types of alcohols in the same molecule. And then I say, okay, now you carry out oxidation, for example, with Petizon's primary alcohol will be less likely to get oxidized than the secondary. Like this, one can involve reduction oxidation based questions. In a similar fashion, one can also incorporate one once you start looking at the C bond formation, then one can think about it that okay, you carry out, say for example, Wittig reaction, and the Wittig reaction gives alpha beta unsaturated ester. Now you reduce the ester, leaving the double bond as it is, and then you have now allylic alcohol. And now if you have another alcohol in the molecule or another a functional group in the molecule, then how that allylic alcohol can be oxidized, or say you have a saturated alcohol and an allylic alcohol becomes aldehyde, then someone one if the other alcohol is in the vicinity, and the stereochemistry, if it is allowed, then it can undergo oxidation to form a lactone. So like this, the questions can be put in. Similarly, various kinds of transformations, including say 3-4 steps. So you have a CC bond formation, reduction, and oxidation, whatever combination, oxidation, CC bond formation, reduction, like that one can do it. So various kinds of transformations can be done, including the basics of the oxidation, reduction, and of course the CC bond formation. Likewise, one can also look at the true and false type of questions. One can look at the true and false, and then see whether it is possible for someone to answer that. Now, what is the question? Kamala, yes, sir. Pankaj rewards. HR Vankar. Please ask a question. Sir, it is pyrolytic elimination. Elimination. Yes. Someone has asked a question. Chem lover. Yes. Elimination. If you have a sulfoxide elimination or selenoxide elimination, it is a syn elimination. So that is the reason why the transition state should have all the 5 atoms, that is sulfur or selenium and oxygen and hydrogen, and of course the other carbon. They have to be syn. Then only the elimination would occur. Okay. Any other question? Chem lover, what is MnO2 based thing? What is it? What is the question? Hello? Yeah. Ravi Dev Yadav. Sir, I do not understand question 8. Please explain, sir, how that confirmation is locked. Tertiary butyl group is not in the fourth. No, 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 no. Tertiary butyl group need not be in the fourth position. Lock means the conformation locking means that conformation cannot be changed. For example, tertiary butyl group is a very large group. It doesn't matter whether it is in third position, fourth position, or second position. Basically, the idea is that one conformation of the cyclohexane undergoes inversion to the other conformation. That means it flips. So supposing if we from one chair to other chair, if it goes, so whatever is axial or whatever is equatorial, it will become now equatorial and axial. So obviously, when you say tertiary butyl group is in equatorial position, doesn't matter if it is the third position or fourth position, the conformation is locked because the conformation cannot change to the other conformation, because in the other conformation tertiary butyl group will become axial, and therefore it is locked. I hope you understand this. Ravi Dev Yadav, do you understand? Please write. Yeah, yeah. Good. I understood. Good, very nice. Any other question? Anybody regarding MnO2? MnO2 allylic oxidation, yes. With MnO2 allylic oxidation, what is the question? Chem lover? Sir, then stereo mention. What is stereo? Please ask the questions explicitly. I'm not able to understand. Allylic oxidation, MnO2. Yes, MnO2 does allylic oxidation. Allylic oxidation means allylic alcohol getting oxidized to the corresponding ketone or aldehyde, whatever it is. You have to ask this question specifically. Yeah. Sir, in case of pyrolytics in elimination, stereo mentioned na. Yes, yes, of course. Stereochemistry has to, like in this particular case, the question number 6, which I have mentioned about it. Here I have not mentioned the stereochemistry. That is very true. So therefore, for example, the elimination to give the exomethylene, that is elimination from the methyl group, is very clear. That has to take place. Now, I have not specifically mentioned about it because we assume that the stereochemistry of the hydrogen here, suppose if the hydrogen here is having the same stereochemistry as the sulfoxide. It is very true. What you are saying is absolutely correct. It has to be pyrolytic in elimination, and therefore stereochemistry has to be mentioned. I have not mentioned stereochemistry because I wanted you to understand that all the three possibilities are there, and between all the three possibilities, which possibilities are likely to take place. Here the question is more related to the fact that the methoxy group or any heteroatom which is present on a carbon which has a hydrogen which can be eliminated. So supposing the hydrogen which is next to the methoxy group is alpha and the sulfoxide is also alpha. Similarly, if the hydrogen which is next to the phenyl group is alpha and sulfoxide is also alpha, so both the hydrogens can eliminate. For the methyl group hydrogens, there is no problem because there are three hydrogens and there is nothing there outside, so there is no problem. So getting the product number 2 is having no problem absolutely. But since I have deliberately not given this, considering the fact that three possibilities are there, out of the three possibilities, two possibilities exist because in the two is anyway I told you why, and four is because of the high maximum conjugation, and third possibility is not there because of the electronic repulsions. I hope you understand this. Otherwise, yes, if I ask a question related to it, stereochemistry has to be mentioned. Pyrolytic. This is a home assignment, therefore I did not mention about it, and I wanted that you should ask such a question. I hope you understand now. Is it clear? Okay, very good. Further question? Whoever is here, they should understand that they have to do all the assignments and ask as many questions as they can. And they can also write their questions to the tutor, and I'll get those questions and I'll answer separately also. There is no problem. So you don't have to wait for 1 month. You can ask the questions as many as you can, whenever you can, so that you understand the questions. The idea is that you have to grasp the whole thing properly. Ask questions further. Yeah. Yes, I have taught this whole course. Why do you why do you ask this question? I have taught this whole course, oxidation, reduction, and some aspects of CC bond formation. Yes, Ravi, why do you ask this question? Any other question? Any doubt? Why is Ravi Yadav asking question like, have you taught this course? Yes, I have taught. Assignments. Why you were not able to open the assignment? Maybe I have to open in desktop. I don't know this part. Uh, I think you have to ask the NPTEL people. You should be able to open. I don't understand why you are not able to open. Yeah, I asked because I was not able to open find assignment, sir. Maybe I have to open in desktop. Did you open in mobile or what? Otherwise, if you are not able to open, then you send me a email or to the tutor or me, and I'll send you separately the assignment. But you should be able to do that. I think you have to ask the NPTEL people. Okay. Any other question? Ortholithia. Oh, ortholithiation is actually not really a part of this course that I have not taught about it. So maybe you can ask specifically a question. Ortholithiation. You have some heteroatom somewhere nearby, and therefore the you ask specifically. You have to ask question. Although I have not taught in this particular course, but I can answer your question. If you ask me separately by email, I can answer your question because this is not related to this course right now. But you have to ask a specific question. Tell me about ortholithation. What specifically you ask me? What is it? You should ask the course related to this course which I have taught so far. Any other question that if you have, you can send me separately. Better that you draw your question by drawing and take a photograph and then attach as an attachment to the email. Yeah. Any other question? Ashok is traveling. Chem lover, Pankaj, rewards. Nobody has asked any question. I hope you understand all the enolates formation and the oxazolidines and the stereochemistry related hydroxylation and other things, which I have taught in the fourth week. You should be ready with the questions and then you post it at the time of interaction. I'm still available online. Any question, please post. Looks that there is no question. Yeah, still about osmium tetroxide, sir. If any OH group nearby and we are reacting with osmium tetroxide, so how stereochemistry is governed? Yes, that will definitely be governed because osmium tetroxide. I will be teaching the next. I have taught about this part which you are asking. So if there is a hydroxy group, that hydroxy group will interact with the osmium tetroxide, and then it will direct the hydroxylation from the same side. If the hydroxy group is not there, then there will be steric hindrance, and it will then go from the other side. So I have taught about this part later on when osmium tetroxide based oxidations are discussed. But yes, it does make a difference because it will have a hydrogen bonding with the osmium tetroxide oxygens. And then whatever is the stereochemistry of the OH group, there from that side the dihydroxylation would occur. Okay, do you understand? Okay. I hope there are other people who are listening to this, and if they have questions, please ask, no matter what kind of question it is pertaining to the this course. Please ask questions. All right, good. I'm glad that you have liked it. I did with osmium tetroxide, then stereochemistry, same like OH group. Otherwise, somehow, well, yeah, that's if you add TMEDA, yes, I think that uh, you have to understand that which uh, no. What does TMEDA do? TMEDA will react with the osmium tetroxide, right? No, I'm not. I don't agree with you. If you have a hydroxy group there, just like say for example, if you have hydroxy group, allylic hydroxy, then your epoxidation with the metachloroperbenzoic acid takes place from the same side. In a similar fashion, when you have a double bond having a hydroxy group, then the hydroxy group will have a hydrogen bonding with the osmium tetroxide, and therefore the this dihydroxylation will occur from the same side. If it is something else like acetoxy or something else, then of course it will be from the other side. So you have to take that into consideration. What is the role of TMEDA? How does it give the same side? Chem lover? You will see that when I'll be teaching that particular path, you will see that the emphasis on that. I hope you understand. Yeah, but it only increases the rate. It will not increase. It will not do anything to the. It gives electron oscillator. Yes, that is true. But in which way does it affect the stereochemistry? See, many times some of these things are added. For example, osmium tetroxide, when it is reacted with pyridine or any other nitrogen, basically what it does is if it is a trivalent, it becomes a tetravalent nitrogen, and it is a positive charge. For example, pyridine, and that is the basis of the making the osmium tetroxide faster, so that your quinidine or those Sharpless-based dihydroxylations are essentially to increase the rate of the reaction and also to make it chiral. But TMEDA is one of the reagents which will just add to this and then make the rate of the reaction faster. But it will not do anything as far as the stereochemistry is concerned. Stereochemistry is you are depending on the OH group, which is you are asking, the question is being asked whether the OH group will affect. Yes, OH group, in which way it can affect? OH, H is that will have a hydrogen bonding with the osmium tetroxide. Osmium tetroxide is a reagent that can attack from the top or from the bottom. So How does it happen? You just imagine the metachloroperbenzoic acid base epoxidation of allylic alcohol versus non-allylic alcohols. So you have the hydrogen bonding with the OH with the metachloroperbenzoic acid. In a similar fashion, yeah, I'll check it. What you are saying is I'll check it, but as far as I understand, it is the OH group which is TMEDA. I will check it, but if you take without TMEDA osmium tetroxide, whichever way it has to be having hydrogen bonded or hydrogen bonding on the top. I will check that what you are asking. I will check in Caruthers, and next time I'll let you know. Chem Lover and Ravi, you both can write a mail to me, and I will respond to you on that. Is it okay? Okay, ask questions. Well, if there are no questions, then we can close the session.
Yes, sir.
Yeah. Okay. If Chem Lover as well as Ravi Yadav, any one of you, if you respond, whether it's okay to close or shall we? You have any questions? Then you can go ahead. Okay. I think we can close it. Okay. Good. Yeah. Okay. Fine. Thank you, Chem Lover. But I think my answer to that was from the Ravi's question whether the OH group makes a difference in also not in the role of TMEDA, but I'll check it with Caruthers and next time I can explain to you. But there could be some other explanation for that, but not just. But the hydrogen bonding is definitely one thing that is important. Okay, shall we close now, Omkar?
Yes, sir.
Okay, fine.
Okay.
All right.
Thank you, sir.
Thank you. Yeah. Bye.